large sea. In the 1970s, the USSR began a project that would push the limits of human exploration, not to the stars, but
Judges. The Kola Superdeep Borehole remains the deepest hole ever dug by human hands. 12,260.
The borehole was a window into a world we had never seen, a world of crushing pressure, extreme heat, and rock that had been frozen in time for billions of years.
The Earth is a layered world. A thin crust of solid rock, a mantle of slowly flowing stone. 12,262 meters. An effort, enough to fit the entire height of Mount Everest with room to spare. The core samples brought up from the borehole revealed a history of the Earth that we had never seen beforehand. Rock that had been buried for 2.7 billion years. The drilling was a feat of engineering, requiring technology that had never been used before. The heat and pressure at 12 kilometers were so intense.
There it is, right there. I see it. That explains the magnetic variance. This changes everything.
The Kola Superdeep Borehole was a journey into the unknown. A journey that raised more questions than it answered.
The Kola Superdeep Borehole was born from the space race, a competition between superpowers to reach the deepest depths of the Earth, mirroring the race to the stars.
In 1970, the USSR began drilling the Kola Superdeep Borehole. The goal? To reach 15,000 meters into the Earth's crust. The site was chosen for a reason. The Baltic Shield, a stable area of the Earth's crust that was expected to allow deep drilling. The drilling was a constant battle against heat, pressure, and the unpredictable nature of the rock below. The deeper they went, the more difficult it became.
At 12 kilometers, the temperature reached 180 degrees Celsius, hot enough to melt the drill bits. The engineers had to constantly.
The core samples revealed something unexpected. Water, trapped in the rock at depths of over 6 kilometers. This water was not like the water we see on the surface. It was thick, dense, and filled with dissolved minerals. The deep rock also contained evidence of ancient life lied, traces of organic matter that had been buried for 2.7 billion years. The Kola Superdeep Borehole was a triumph of human curiosity and engineering, but it was also a reminder of how
in tears. The descent into the Earth began with a single hole tapen, a narrow, dark shaft that would eventually plunge 12,000.
As the drill bit descended, the temperature rose by 1 degree Celsius for every 100 meters. At 1,000 meters, at 5,000 meters, the pressure was over 500 atmospheres, enough to crush a human body in an instant. Yet the rock continued to reveal its secrets. The rock at 10,000 meters was over 1 billion years old, at a time before complex life existed on Earth. Every centimeter was a journey through history. At 12,000 meters, the temperature reached 180 degrees Celsius, hotter than boiling water. The engineers had to develop new technologies to withstand the heat. Special alloys and cooling systems that had never been used before. The Kola borehole was a journey through time, through billions of years of Earth's history. Each meter was a step back into the deep past. The descent was a journey into the unknown, a journey that revealed the hidden world beneath our feet. But it was only the beginning. Beneath the crust lies the mantle, a layer of rock so hot that it flows like honey, driving the movement of the Earth's continents and the eruption of volcanoes. The mantle is a world of slow motion, rock that moves at the speed of a growing fingernail. The mantle is composed of peridotite, a dark, dense rock rich in olivine and pyroxene. It is the most common. The mantle is 2,900 kilometers thick, nearly half the Earth's radius. It is a vast, slow-moving. Mantle plumes are the Earth's internal plumbing, columns of hot rock that rise from the deep mantle and create volcanic hotspots like Hawaii and Iceland. The temperature in the mantle varies from 1,000 degrees Celsius at the top to over 4,000 at the boundary with the core.
The mantle is not a distant, abstract concept. It is the engine that drives our planet, the source of the heat that fuels.
The mantle is a treasure trove of minerals, olivine, pyroxene, garnet, and even diamonds, formed under the immense pressure of the deep earth. The mantle is the heart of the earth, a vast, hidden world of heat and pressure that shapes our planet in ways we are only beginning to understand. The Moho Discontinuity is one of the most significant boundaries on Earth, the invisible line that separates the crust we live on from the mantle below.
The Moho was discovered in 1909 by Andrija Mohorovičić, who noticed that seismic waves suddenly accelerated.
The Moho is not a sharp line, but a transition zone where the rock changes from granitic to peridotite. The Moho is closest to the surface beneath the oceans, where the crust is thinner. Beneath the continents, it lies much deeper. The Moho has been a target for scientists for decades, a goal that has proven to be just out of reach. The Kola borehole came close, but it distant. The increase in seismic wave speed at the Moho is a clear signature of the change in rock composition. Beneath the oceans, the Moho is only 5 to 10 kilometers deep, close enough that scientists have dreamed of drilling through it to reach the mantle. The Joe's Resolution is one of the ships that has attempted to drill through the ocean crust to reach the Moho. Stanfleece. The rock above the Moho is gabbro, a dark, dense rock that forms the lower layer of the oceanic crust. The Moho is the final frontier of Earth exploration, a boundary that separates the familiar from the unknown. Below the mantle lies the outer core, a vast, churning ocean of liquid iron and nickel, as hot as the surface of the sun. The motion of the liquid metal in the outer core generates the Earth's magnetic field, a shield that protects us from the solar wind and cosmic radiation. Earth. The outer core is not a calm ocean. It is a turbulent, chaotic sea of molten metal, driven by the heat of the inner oceans. The magnetic field generated by the outer core creates the aurora, a beautiful, glowing display of light that reminds. The outer core is 2,200 kilometers thick, a vast ocean of liquid metal that surrounds the solid inner core like a shell. The outer core is about 85% iron and 15% nickel, with traces of lighter elements like sulfur and oxygen. The convection currents in the outer core are driven by the heat of the inner core, a self-sustaining cycle that has been running for billions of years. The magnetic field generated by the outer core is not static. It shifts, moves, and even reverses directions. The Earth's magnetic field behaves like a giant bar magnet. With the South Pole near the geographic North Pole, the outer core is the heart of the Earth, a liquid engine that has been running for billions of years, generating the magnetic field that makes life on our planet possible. At the center of the Earth lies the inner core, a solid sphere of iron and nickel, as hot as the surface of the sun. Under the immense pressure of the Earth's core, the iron atoms are forced into a hexagonal, close-packed structure. The temperature at the center of the Earth is over 5,000 degrees Celsius, hot enough to melt steel. But the pressure is so immense, the inner core spins at its own rate, slightly faster than the Earth's surface. This super-rotation is infinite. The inner core is made of an iron-nickel alloy, similar to the metal found in iron meteorites. These meteorites, the extreme pressure and temperature of the deep Earth can create diamonds, a reminder of the forces that are constantly at work beneath our feet. The inner core is the heart of the Earth, a solid sphere of iron and nickel surrounded by the liquid outer core. The density of the inner core is over 13 grams per cubic centimeter, nearly twice the density of lead. It is the densest material on Earth.
The inner core is a hidden world, a place we will never see with our own eyes, yet it is the heart of our planet.
The inner core is the heart of the Earth, a solid sphere of iron and nickel, as hot as the sun, yet hitchelsistomilzingt. The Earth is a living planet, a world of immense heat, driven by the decay of radioactive elements and The heat of the Earth comes from two sources: the decay of radioactive elements like uranium and thorium, and the residual. The heat of the Earth is visible at the surface, in the lava that flows from volcanoes, the steam that rises from geysers. The heat of the Earth moves in three ways: conduction through the solid rock, convection in the flowing mantle, and radiance. The temperature at the center of the Earth is over 5,000 degrees Celsius, hotter than the surface of the sun, yet the crust. The heat of the Earth is not just a scientific curiosity, Forbris. It is a source of energy that we are only beginning to tap into. The heat of the Earth is the engine that drives plate tectonics, the movement of continents, and the creation of mountains. The heat of the Earth is captured in the rocks it creates. Obsidian, basalt, granite, and even the heat of the Earth is a reminder of the forces that shape our world. Forces that are still active, still moving, still creating. The heat of the Earth is the heartbeat of our planet, a hidden, powerful force that sustains life. The inner core is not a static sphere. It is spinning, slightly faster than the Earth's surface itself. The superrotation of the inner core is thought to be linked to the Earth's magnetic field, a connection that scientists are still trying to unravel. The inner core rotates about 0.1 degrees per year faster than the Earth's surface. Over a century, the spinning of the inner core within the liquid outer core is the engine of the Earth's magnetic field. A complex, the aurora is a visible reminder of the invisible forces at work deep beneath our feet, a dance of light and energy that connects the core to the surface. The spin of the inner core may also affect the alignment of its iron crystals, creating a unique fabric that records the Earth's history. The twist is that the inner core is not a passive sphere. It is an active, spinning engine. That the spin of the inner core is not just a curiosity, Formix. It is a key to understanding the Earth's past, present, and future. Recent studies suggest that the spin of the inner core may not be constant. It may speed up or slow down over time. The twist is that the center of the Earth is not a quiet, frozen place. It is a dynamic, spinning world. We have never seen the Earth's interior with our own eyes, yet we know more about it than we do about the deep ocean. Earthquakes are nature's X-rays. Every time the ground shakes, waves of energy travel through the Earth, carrying information about the layers they pass through. Seismometers around the world record the arrival of seismic waves. By measuring the time it takes for different waves to arrive, by combining data from thousands of earthquakes. Seismic waves are not the only source of evidence. Occasionally, volcanic eruptions bring up pieces of the mantle face, direct samples of the deep Earth. The mantle is not completely sealed. Volcanic eruptions bring material from deep within the Earth to the surface, giving us a glimpse of the world below. The evidence is clear. The Earth is a layered planet, with a solid crust, a flowing mantle. The magnetic field itself is evidence of a liquid outer core, a layer of molten metal that acts as a dynamo. Iron meteorites are fragments of the cores of other planets, a rare glimpse into the composition of planetary interiors. They match the Earth's core almost perfectly. The evidence is all around us, in the earthquakes we feel, the volcanoes we see, and the magnetic field that print. The Earth's core was formed over 4.5 billion years ago, during the planet's violent infancy. As one theory suggests that the Earth's magnetic field reverses direction every few 100,000 years, a phenomenon that is recorded in the rocks of the ocean floor. The leading theory for the generation of the Earth's magnetic field is the dynamo theory, a process in which the motion of the liquid outer turrets. Another theory suggests that the inner core is still growing, slowly, over billions of years. As the Earth cools, the extreme pressure and temperature of the deep Earth can create diamond's pulse, a reminder of the forces that are constantly at work beneath our feet. Some theories suggest that the interaction between the core and the mantle is not a one-way process. Material from the core may rise to the surface through mantle plumes. The strength of the Earth's magnetic field is directly linked to the temperature of the core, a relationship that scientists are still working to understand fully. The magnetic field generated by the core acts as a natural barrier, deflecting the solar wind and charged particles away from the rocks of the Earth's crust. Preserve a record of past magnetic reversals, a history of the core's behavior that stretches back millions of years. The theories are a testament to the power of science, a way of understanding the invisible forces that shape our world. The leading theory begins with a global magma ocean, where molten iron and nickel sank toward the center under gravity. As the newborn Earth cooled slightly, dense metallic droplets formed, then sank through the molten rock like heavy rain. Some models suggest the core formed from iron-rich planetesimals that arrived early, while others propose iron separated from a primitive mantle. In the magma ocean model, the surface cooled slowly, while deep below, heavy metal continued its descent for millions of years. The mantle contains far fewer iron-loving elements than primitive meteorites, suggesting those elements were pulled into the core. Hafnium-tungsten dating reveals the core separated within roughly 30 million years of the solar system's formation. How deep that magma ocean reached remains debated, but some evidence points to a very thick, planet-scale layer of molten rock. The solid inner core was not present at the beginning. It may have begun crystallizing from the liquid outer core much later. A later rain of meteorites may have delivered the precious metals now found in the mantle, long after the core had formed. The exact sequence remains uncertain, but every theory points to the same conclusion. The core holds Earth's deepest origins. Our modern understanding of Earth's interior comes from listening to earthquakes as their waves travel through the entire planet. Primary waves compress and expand rock, while secondary waves shake it sideways, and these two travel at very different speeds. Secondary waves cannot travel through liquid, so their absence on the far side of the planet revealed a liquid outer core. Primary waves slow through the liquid outer core, then speed up again, revealing a solid inner core hidden at Earth's center. The broad structure is now agreed: a thin crust, a thick solid mantle, a liquid outer core, and a solid inner core. Laboratory experiments and meteorite comparisons give estimates of core composition, mostly iron, with nickel and a small amount of lighter elements. The scientific consensus is that the core generates Earth's magnetic field through the motion of liquid iron in the outer core. What remains uncertain is the exact amount of lighter elements in the core, its precise temperature, and how fast the inner core grows. Estimates suggest the inner core began solidifying between 1 billion and 500 million years ago, but the exact timing is still debated. The scientific consensus is strong on the broad picture, but many fine details of the deep Earth remain unknown and still waiting to be discovered. The deepest hole humans have drilled is just over 12 kilometers, a tiny scratch compared to the 6,000 kilometers to the core. To go deeper, engineers are developing new drill bits that can survive extreme heat and pressures far beyond current limits. At the base of the crust, pressures exceed 1 million times atmospheric pressure, and temperatures surpass 400 degrees Celsius. Future missions might use autonomous capsules that cool themselves while drilling through rock too hot for human-made equipment to survive. Since direct access is impossible for now, scientists rely on seismic waves from earthquakes to probe the deep interior remotely. A new generation of dense seismic arrays and satellite measurements is giving us an increasingly detailed picture of the core without leaving the surface. The mantle, though solid, flows slowly over millions of years, and any borehole through it would be squeezed shut almost immediately. If we ever bring back a direct sample from the mantle, it would answer fundamental questions about Earth's composition, age, and evolution. Some proposed concepts imagine a probe that could survive long enough to transmit from the outer core before being destroyed, sending back a final burst of data. The core may always remain physically out of reach, but the human drive to understand it will continue to push the limits of exploration. Despite decades of study, the deepest parts of our planet still hold secrets that science has not yet been able to solve. One of the biggest remaining mysteries is the exact composition of the inner core, which affects everything from its age to its growth. The inner core may rotate slightly faster or slower than the rest of the planet, a subtle motion that scientists still struggle to measure. Magnetic field reversals, when north and south poles swap, remain unpredictable and poorly understood events in deep Earth history. The crystal structure of iron at the core's center may be more complex than we thought, with defects that affect heat and magnetism.
Heat flow from the core to the mantle is uneven, and scientists are still mapping the mysterious hot and cold regions of the deep Earth.
Giant structures at the base of the mantle, hundreds of kilometers tall, may be remnants of ancient processes we don't fully understand. Each new earthquake provides another glimpse into the core, but the picture remains incomplete, leaving room for new discoveries. The more we learn about Earth's core, the more we realize how much remains hidden beneath our feet. The file is closed. the mystery remains.